is finish up this sigma definition. And there's only two problems that I would like to do. And I just got to find one of them. Let's see. That's not it. That's not it. It's not it. It's one of these two here. Okay, and we need that one, but the one I want is this one here. So, let me minimize this, open up. So this kid, who I never got to finish, he never kept his next appointment, had this problem that if y is equal to 4x squared plus 2x, find the area under the curve from 0 to 2 using the limit definition. In fact, the problem said using all three definitions. In other words, they wanted him to do it using rectangular approximation method. They wanted him to do it using the integral sign. And they wanted him to do it using the definition of the sigma definition. So let's start with delta x.
Are we doing all three or just the...
No, we're just going to do the sigma definition. Okay. I know that the integral definition, you know how to do these. We don't need to review that. That's just using the power rule and evaluating between 2 and 0. Okay. And the rectangular definition, we've done enough of those also. But what we haven't done very many is the sigma definitions. So the way you always start out a sigma definition is figuring out delta x. Well, delta x is one limit or one limit of integration minus the other. In this case, from 0 to 2 would be 2 minus 0 is the numerator. And we're going to divide that area up into n rectangles. So the width of each rectangle is 2 over n. So delta x is 2 over n. That's always the first step. Now, since the area under that curve by definition is equal to the limit as n goes to infinity of sig...
X sub I thing and everything? Or is that for the C sub I?
We're getting to that, right.
Oh, okay. That's
okay. In other words, this is f of c sub I times delta x. That's the definition of it. That's the general definition. Okay. The question is what is c sub I? Well, according to this, the second thing they figure out is what is x sub I, which is the same thing as c sub I. Okay. This teacher uses x sub I, my book uses c sub I, but it means the same thing. It means some point in the ith interval.
Okay.
And in fact, for this one, they're not using just some point, they're using the right-hand end point.
Okay, so I'll put using right end point.
They're using right-hand endpoint, which means, and let me use x sub I here instead of c sub I. Well, what is x sub I for the right-hand endpoint? Well, it's a...
I'm just going to put c sub I so I don't get confused from my previous...
Okay, that's fine. Let me go back and use c sub I then.
Okay, I just don't want to...
Okay, no, I agree. Although it is important to understand that We're talking about a point on the x-axis that is in one of those rectangles that we have split that area up into.
Right.
Which rectangle? The ith.
The ith one. Okay.
Either the first, the second, the third, the fourth, the fifth, the sixth, the ith one. Okay. So if, I'll just draw it again, this function, some cubic function, it may look like that. Okay, so let's assume that it looks like that. Well, there's 0, there's 2. We're going to break this thing up into n rectangles. And our c sub ith is going to be the right-hand endpoint of one of those rectangles.
Now, is this, when you say we're breaking up into rectangles, is it really intervals that we're breaking up, or are we still using rectangles?
We're still using rectangles.
We're still using rectangles.
Still using rectangles. Okay.
Okay.
The key is knowing how to define this c sub I. Well, where is this c sub I? If each one of these is delta x, then that's 0 plus 2 delta x's. Right?
Let's see. Yeah, that's c sub I. Yeah.
So it's
right.
a plus the interval times delta x. In other words, if that c sub I was in the third rectangle, it would be a plus 3 times delta x.
Okay.
If it was left endpoint, it would be a plus I minus 1 times delta x. Notice that if I make that c sub I instead of the right endpoint, the left endpoint, well, now it's only 1 delta x away from 0.
Right. So
and yet it's still the second rectangle. So the only way to get 1 out of that is to do I minus 1. In other words, I would be 2 minus 1. We would have the proper number of delta x's, defining c sub I. Okay? So I'm going to use the right-hand endpoint for this problem. And a is 0 because we're going from 0 to 2.
Okay.
And I don't know what I is. It's the ith interval, but I know what delta x is. Delta x is 2 over n. So c sub I is 2I over n. You with me?
Okay, 1 sec here. N. So that needs to 2I over n. Yeah, okay.
Okay, so we have c sub I defined as a function of I and n. Well, if we go back to this definition, we want f of c sub I, so it's really f of 2I over n. Right?
Okay. Yep.
In other words, all I'm doing is substituting that for that. So what I really want is the limit as n goes to infinity of sigma as I goes from 1 to n of f of 2I over n delta x. Step 1.
Okay.
And in place of delta x, I know that that's 2 over n, so let's go ahead and write that as 2 over n. And notice now I'm going to end up with a function that is nothing but i's and n's. Well, my function is f of x equals 4x cubed plus 2x. Okay.
Okay.
So this becomes the limit of, as n goes to infinity, of sigma as I goes from 1 to n. Well, what is that? That is where I substitute what's inside the parentheses for x in the function. So it would be 4 times 2I over n, my c sub I, cubed, plus 2 times 2I over n, times 2 over n.
Oh, I had it squared. That's cubed.
Right. Yeah, the original function is cubed.
Okay.
4x cubed plus 2x.
Okay.
And let's see, this whole thing actually has to be multiplied by 2 over n. Notice that 2 over n is delta x. So this thing has to be f of 2I over n times 2 over n. So what I have in brackets there is just the f of 2I over n.
Okay.
And then I'm going to multiply that by 2 over n. Okay, so now we do the algebra. In other words, we simplify this as much as we can. We haven't lost the sigma yet. We're not going to lose the sigma until we go to our summation formulas. Then we'll be able to convert and get rid of the sigma and come up with numbers. Well, let's see, what's that cubed? 8I cubed over n cubed times 4. That becomes 32I cubed over n cubed. This number right here. This part here becomes 4I over n. And we're going to multiply it all by 2 over n. If we distribute that, we get 64I cubed over n to the 4th plus 8I over n squared. This is a typo here. Notice that in the paper that I took the picture of from the student, they distribute the 2n to get 64I cubed over n to the 4th, but then when they distribute it here, they forgot to write the 8, or it actually looks like somebody went in and erased it.
Huh.
There's an 8 right there where my hand is.
Yeah.
2 over n times 4I over n is 8I over n squared. And in fact, the 8 comes back in the very next row, so that's why I know it's a typo.
I got you.
Okay. Now, what I can do with these sigma of sums is to separate it into a sum of sigmas. And furthermore, I can take the n outside the sigma because the n is a constant. You have to always remember that these, in the sigma definition for area under the curve, n is a constant, even though it looks like it's a variable. I mean, we have I going from 1 to some unknown n, and n is going to approach infinity. If that doesn't look like a variable, I don't know what does. But
that's what I was thinking, yeah. Since it says n goes to infinity, yeah. I guess that's what gets confusing sometimes.
Well, remember what our first step was here. Our first step was we broke that area up into n rectangles.
Right.
That makes n a constant.
I guess so, but then one could argue that you're adding more and more n's as n goes to infinity.
Right.
You're slicing it
Right,
up.
which
So
appears
you
to
could say
make
it's
it
a
look
variable.
like a variable. Yeah, I know.
Yeah.
But I don't know how they get away with doing this, to be honest.
It's just
It must work. I mean, that's
Yeah.
the proof of the pudding. So
Yeah.
I can take both the...
And we're going to distribute the sigma as well?
Well, no, we're going to separate this into the two following. We're going to take the 64 and the n fourth outside the sigma, leaving behind I cubed, plus another sigma with an 8 over an n squared outside the sigma times I. In other words, the only thing you want left in your sigma is I or I squared or I cubed or I to the fourth. Because we have summation formulas for each of those. Here's our summation formula. There's what I is, there's what I squared is, there's what I cubed is. And it's all we're going to do is substitute that for the I that we have. So for I cubed, in other words, now I'm going to get rid of the sigma also. This becomes 64 over n to the fourth times n squared times n plus 1 quantity squared over 4.
The limits are still in there. It's still all to the limit of n, is that right?
No. Oh, yes, it's still, we're going to figure out what this thing is as n goes to infinity. Yeah, I didn't write the limit. I need to. Thank you. The limit as n goes to infinity of this whole thing plus 8 over n squared times sigma of I is this, n times n plus 1 over 2. And now we're going to actually figure out what number this comes up to. Let me get rid of this page. We don't need this page anymore. Well, this numerator right here that you see is what you get when you expand n plus 1, you square it, and multiply it by n squared. So just follow me over here. Here's our 64 over n to the fourth. This term is what I cubed, sigma I cubed turns into.
Okay.
Plus 8 over n squared. And this is what sigma I turns into. Well, what is all of that together? It is the limit of, if I distribute all of these, notice that the only term that does not end up with an n in the denominator is the first one. I get 64 n to the fourth over n to the fourth. Well, that's 64. When I distribute this quantity to the middle term, what do I get? I get 64 divided by 4 times 2. Anytime I end up with the n in the denominator, I know that term is going to 0. In other words, I actually end up with 128 over n when I distribute. When I multiply 64 over n to the fourth by 2n cubed over 4, now I over 4n, okay? But whenever I have an n, a net n in the denominator, I know this term's got to go to 0 as n goes to infinity. So I don't even care what the numerator is or what any of the numbers are. As long as I know that there is a net n in the denominator, then that term is going to 0.
I guess I just have to work out the math of all that later. So basically, we just did a bunch of math, and then it came out as 64.
Here's what it came out as. Let me write it. 64 n to the fourth over n to the fourth. That's multiplying that by that. Excuse me, over 4n to the fourth. Plus, second term is 128n cubed over 4n to the fourth. And the third term is 64n squared over 4n to the fourth. So this is what I get when I distribute this to this. Okay. Now, as n goes to infinity, this thing goes to 16. The n to the fourth cancels with this n to the fourth, and all I'm left with is 64 divided by 4.
Okay.
When n goes to infinity here, the denominator blows up more than the numerator because I got a net n in my denominator. So that goes to 0.
Okay.
Same thing with that term. I got an n to the fourth in the denominator. I got an n squared in the numerator. That's going to go to 0 also. So the only other term I have is this term. In other words, we just did this term here.
Yeah, right.
Well, if we do the same thing over here, we get 4. You can see right away that we're going to have an n squared, which is going to cancel out with this n squared. And so we're going to get an actual number, 8 over 2, 4, and the other terms are going to all go to 0 for the same reason these other terms went to 0 over here. In other words, this is multiplied by the 1 is an n. We're going to have an n in the numerator, an n squared in the denominator. That term's going to 0.
I see. I don't know how to write that in order to remember it, but anyway.
Well, just always remember that if your denominator has the number that's going to infinity, then it's going to 0. As long as there's no equivalent, I don't even want to say variable, as long as there's no equivalent n in the numerator.
Okay. All right, and then so that goes to 4.
Mm-hmm.
Okay.
Okay. All right, and so that's how you do a basic function. Because all we did was we took a relatively basic function, 4x cubed plus 2x, and we used the sigma limit definition to figure out that the area was 20. And that's an exact area. That's the same area you get if you take the antiderivatives of this and evaluate it from 2 to 0. In other words, that's an exact area. That's not any longer an approximation because n is going to infinity. In other words, we're going to end up with an infinite number of rectangles in there. It's kind of interesting, actually, the way this works out. I don't know how anybody ever came up with this. You start out treating n like it's finite. In other words, delta x is b minus a divided by n. N looks finite. And then after you go through all the math and the algebra, then you end up using n going to infinity to come up with the answer.
Right.
But the fact that n's going to infinity is what tells you that your answer is exact. The only thing we haven't really determined yet is whether it matters whether you do left endpoint or right hand endpoint.
Okay.
Because as all we just proved is that the right hand endpoint, which is how this is defined, gives you the same area as the integral definition does, as the fundamental theorem of calculus does.
Okay.
Okay, so we now know that this sigma limit definition is the same as long as you use right hand endpoint.
Okay.
Well, we're not really going to prove that any point works, but we're going to prove that left hand endpoint gives you the same number as right hand endpoint. Which is interesting because I wonder how they actually do prove that it doesn't matter where the point is. In other words, it does not matter where C sub I is in that rectangle. It can be left hand endpoint, it can be right hand.
Well, the idea is that if they go infinite ends, at some point the left and right endpoint, it's just going to be one point.
Yes, no, I agree. I agree totally. And it makes perfect sense logically. But proving it mathematically is what I'm curious as to how Riemann did that. In other words, let's do one more problem using the same logic, only our function is going to be a little bit easier. It's just going to be x squared. And we want the area under the curve from 0 to 2. So first step is delta x equals 2 over n. In other words, delta x is really equal to b minus a over n, which in this case is 2 minus 0 over n. And now let's talk about c sub I. For right hand endpoint, it's a plus I times delta x.
Which we didn't establish an interval, did we yet? Or
yeah, 0 to 2.
Oh, okay.
Okay. For left hand endpoint, c sub I is a plus I minus 1 times delta x. I mean, there's nothing, we're trying to prove if they produce the same answer.
Okay.
And they do, but it still seems to me that as far as a rigorous mathematical proof goes,
okay,
we haven't proved the middle points do the same thing. But maybe based on what you said, you're right. If we can prove it for left hand and right hand, and as n goes to infinity, the left hand endpoint approaches the right hand endpoint. So in a way, I guess that takes care of all points in between.
Makes sense.
Okay, so let's do the right hand endpoint. So that would be the summation from n.
Oh, I see. We're doing both. Okay.
Yeah, we're going to do both to make sure we get the same answer.
Okay. Oops. Okay.
So it's I going from 1 to n. We're going to take the limit as n goes to infinity of f of c sub I. Well, that's 0 plus I times 2 over n. So that's f of 2I over n, just like the last problem we had. Let me erase that and move it down as soon as we get an answer for this. Then we'll do the left-hand endpoint and compare our two answers. Well, here's our function, x squared. So we need f of this instead of x. So this is equal to the limit.
Wait, how do we get the 2I over n again?
That's what c sub I is equal to. A, which is 0 in this case,
okay.
plus I times delta x, which is 2 over n. So this becomes 2I over n. C sub I equals 2I over n.
Oh, I see. Okay, right.
And we want the limit of sigma of f of c sub I. So it's f of 2I over n. Well, that still have sigma in there. F of 2I over n, I'm going to plug 2I over n for x. So I have 2I over n squared times delta x, which is 2 over n, which is okay, I'm going to take all numbers and n's outside. Well, this gives me 4i squared over n squared. So I'm going to have an n cubed of 4 and 8 n cubed outside the sigma. And what I have left is going to be I squared. Now make sure you see how I get from that to this.
Let's see. 8,
I can write the intermediate step there if it's helpful.
I'll just say, put down, do some math or something.
In other words, if you square this and multiply it by that, you get 8i squared over n cubed. At which point I'm going to take the 8 over the n cubed outside the sigma.
Right, okay.
And this is still as I goes from 1 to n. And finally, we're going to use the summation formulas. We're going to use it for I squared in this case, which is this one over here. So we still have the limit, as all this does is gets rid of the sigma. In other words, we're going to lose the sigma in one step, and then we're going to lose the limit in the next.
Okay.
This just loses the sigma. Still 8 over n cubed, and the sigma of I squared is this whole thing here. So I'm going to multiply that by n times n plus 1 times 2n plus 1 over 6. That's what sigma I squared is equal to. Now, again, as all of these do, I have to multiply these out and multiply by this. And I think you can see that by the time I multiply those three numerators, I've got a 2n cubed. Right? In other words, n times 2n is going to give us a 2n cubed. And so when I multiply this by the highest degree of n in the numerator, I'm going to have 8n cubed all over 6n cubed.
Okay.
Excuse me, I'm going to have 2 times 8n cubed over 6n cubed, because of this 2 here. In other words, I could go through and multiply these out, but you don't really need to, because the only term that produces a number is the first one. All of the other terms are going to have an n in the denominator that doesn't go away, and when I take the limit of that, that term goes to 0. So this term here, which I produced by multiplying that times that times that, gives me 16 over 6, or 8/3.
Now the 2 came from the 2n plus 1 there? The 2 times?
Yeah.
Okay.
In other words, that first step, you multiply n times that, you get an n squared. Now when you multiply n squared times 2n, you get a 2n cubed. So there's my 2n cubed. And then I multiply it by 8 and divide it by n cubed, and I throw in the 6, so I get this. And when I take the limit of that, as n goes to infinity, it goes to 8/3. When I take the limit of every other term, notice the second term. N times 1 is n. Times 2n is 2n squared. So now I'm going to have 8 times 2n squared over n cubed times 6. That's my second term.
Wait, what is second term as opposed to what now?
All right. I'm confusing the issue because I didn't do all this multiplication. Let's multiply that out.
Well, I mean, I thought we were done with the whole thing, and it went to...
Well, we are, but...
8/3?
Okay, n times n plus 1 is that.
Right.
Multiply that by 2n plus 1.
Right.
Over 6. Okay.
Yeah, I saw what you said, but it was good. N cubed was the highest
Right,
term.
and every other term has less than n cubed in the numerator. And I still got this n cubed that's going to be in the denominator of every other term. So as long as the denominator has an n greater than squared, all of those terms are going to go to 0. The only term that does not go to 0 is multiplying that times that gives you 2n cubed. Now that n cubed wipes out this n cubed, and I end up with 16 over 6, or 8/3, plus 0 plus 0 plus 0. The other 3 terms that would all have an n left over in the denominator.
Okay, I get it. 8/3 plus 0 plus 0 plus 0. Okay, alrighty.
All right. So we get 8/3 doing it using the right-hand method. And remember that we got the right-hand method by using this formula. It's only the right-hand endpoint where c sub I is equal to a plus I times delta x. The left-hand endpoint method, c sub I would be equal to a plus I minus 1 times delta x. Okay, so c sub I is equal to 0 plus I minus 1 delta x is 2 over n. So c sub I would equal 2I over n minus 2 over n. This is a 1, not an I. And it's a 1 because the left-hand endpoint effectively makes it one rectangle closer to A. Okay, and then we want the limit as n goes to infinity of sigma of f of c sub I delta x. Well, this is our new c sub I when we're doing left-hand endpoint analysis. So it's sigma of f of 2I over n minus 2. I guess I can write it like that. Common denominator.
Okay.
And now I have to evaluate what f of that is for the function f of x equal x squared. So I basically have to square this. So it's still sigma of 2I minus 2 over n squared. The limit of that as n goes to infinity. I can take this 2 out. I can factor that 2, make it look like this. As long as I still leave the 2 inside the squaring.
Okay, now there we subbed in the, what was it, the function
We
was,
plugged in what c sub I was for x. In other words, we need to find f of c sub I.
what was the function? Let's see. Which function were we doing here? What was it?
Y equal x squared.
Oh, okay, x squared. All right, so it was just x squared.
Yeah.
Okay.
And then I still have the delta x as part of, in other words, this delta x is still part of the definition, but now we know that delta x is 2 over n. If we do this algebra, we get 8 over n cubed. You can certainly see how we're going to end up with n cubed times I squared minus 2I plus 1. For the person that decided to use I as a variable in math was short-sighted, because it's really difficult on problems where you have ones and i's. In other words, if I do that math, if I expand that, square it, multiply it by 2 over n, this is what I get.
Okay. Squared minus 2. Okay.
Okay. And now, again, I'm going to remove all the n's and the numbers, and I'm going to be left just with i's, or a number, which I know how to use the summation formulas to convert that. So this is the same thing as a over n cubed times sigma of I squared minus 2 sigma of I plus sigma of 1. And I'm still taking the limit of that as n goes to infinity. And these, of course, are all I equal 1 to n.
Okay.
You see what I did is all I did was I took the numbers and n's outside sigma, and I left behind just the i's or a number.
Okay.
Okay? So this becomes the limit of this. I'm going to replace that with that. N. In other words, I'm going to lose the sigma. It's n times n plus 1. Hold on. What is it? It's n times n plus 1 times 2n plus 1 over 6. That's the I squared. That's what this is this. When I lose the sigma, I replace it with n's. Well, that's really funky, isn't it? The fact that I mean, think about this for a second. The fact that I can take the n outside of the sigma and then replace the I squares or I cubes or whatever has I in it with more n's and then combine the two.
Right.
In other words, it appears that we're treating n as a constant, but it's kind of a semi-variable when I squared is equal to this. So, but I guess that's the way it works.
Yeah, that's sometimes I don't understand when they treat stuff as what, and it gets kind of a little mystifying. But I guess
the middle part becomes 2 times n plus 1 over 2. That's the summation formula for sigma I. And finally, the sigma 1 turns into an n. Still there, Timur?
yeah.
Oh, okay.
Just
I heard some background noises there. What
yeah.
if I'd lost audio or not? Okay, so now I have merely replaced sigma of some I to some exponent with its equivalent summation formula. In other words, with one of these things. There's the 3 summation formulas. And I don't know what I to the 4th is. If you had a problem with I to the 4th, I guess you'd have to... I to the 4th must be I squared times I squared. So I guess you could take this and multiply it by itself to come up with I to the 4th. I think. Yeah, no, that's... You could do that for sure.
Maybe I suppose so. You could just bootstrap them that way. You just build on them.
Yeah, right.
Can you,
Just multiply that times this, really. Yeah. Okay. So now we have this, and without boring you with the algebra, again, you can kind of see what's going to happen. When I distribute this to this, there's only going to be one term that has an n cubed in the top. All the others are going to have a greater power of n in the denominator. You see why? I mean, before, that's an important thing to see.
I think I saw it in one of the problems I did. Let's
Well,
see.
let's multiply this. This
Oh
is
yeah, the rest of them.
n squared plus n times 2n plus 1 over 6. And then I'm multiplying that by 8 over n cubed.
Right.
Okay, well, I got to FOIL these two things. What do I get when I FOIL them? The first term is 2n cubed. The second term is n squared. The third term is 2n squared. And the fourth term is n. All over 6, all times 8 over n cubed. Notice that the only term that loses the n completely is that one. I'm multiplying by 8 over n cubed.
Okay.
So my final answer is going to be the limit of 16 over 6 plus 8 over 6n plus, and it doesn't really matter what the numerator is, 16 over 6n squared plus 8 over n cubed. I got one too many terms there. It's those two terms right there. Those three terms there. Now, when I take the limit of these three terms, as n goes to infinity, the only one that results in a number is that one. Anything that has an n in the denominator is going to 0. So that goes to 0, that goes to 0, and I end up with an answer of 8/3. Same answer I got when I used a C based on right-hand endpoint.
Let's see now. How did we get to 16.6? Just we looked at. Oh, there's a 2 and an 8.
Not right.
Okay.
There's a 2, an 8, and a 6 that make up the 16/6, and the n cubed cancels out with that n cubed.
Right. Okay, highest degree.
And because this is less than n cubed, and that's less than n cubed, and that's less than n cubed, all of those terms are going to end up with an n in the denominator, which means that term's going to go to 0. So I don't really care what the numerator is. In other words, I'm not going to go through and put in the algebra to figure out what the numerator is. I don't care if that's 8 over 6 or that's 16. It doesn't matter.
Okay.
Okay.
Okay, so we got the same answer.
So the left hand is the same as the right, which is kind of interesting because C sub I is significantly different. In other words, in one case, C sub I was A plus I times delta X. And in this case, C sub I is A plus the quantity I minus 1 times delta X. So it's a quite different C sub I in both cases, and yet they both produce the same answer.
Yeah, right.
Which you would expect, as long as this is giving you an exact answer and n is going to infinity, it should be the same answer. Whether we have just proved that it doesn't matter where C sub I comes in that rectangle, in the ith rectangle, or not, I'm not sure. Perhaps. Perhaps it kind of relates to the intermediate value theorem, and the fact that if it's the same for the left-hand endpoint and the right-hand endpoint, and as n goes to infinity, the left-hand endpoint approaches the right-hand endpoint, then perhaps that's proof that any C sub I will do. there still is further considerations in terms of that. In other words, not only will any C sub I do, but any width does. I don't need consistent widths. I can break this thing up into all kinds of rectangles that have different widths. As long as n goes to infinity, then it doesn't matter that these widths are different. Now, we haven't really talked about that. We haven't presented any proof of that at all.
Well, although the delta x, isn't that uniform that they bake into that formula?
Well, yeah, in the sigma definition, delta x is the same. In other words, it really does require that the width of each rectangle be the same.
Okay.
Okay, in other words, when I'm doing my sigma definition, I start off by saying delta x is the interval divided by the number of rectangles, which means that the width of each rectangle has to be the same. Each of these is delta x. And so I'm going to take my interval and divide it by the number of rectangles, and that's what delta x equals.
Okay.
And that's the very first step of doing that. But, in fact, and I don't know where the proof of that is. I imagine that's a pretty hard proof, but you can prove that the C sub I can be anywhere. It doesn't have to be on the right-hand endpoint. It doesn't have to be on the left-hand endpoint. It can be in the middle. It can be there. It can be anywhere in that rectangle.
Right. So if it can be anywhere in the rectangle, you're saying you could break the rectangles up any way you wanted to into...
Well, that's something different. Again, I'm not sure that's provable by this. Probably is, but I wouldn't know how to begin, because the proof, in other words, all of these start out with stating what delta x is.
Right, right.
And if you're going to allow the width of the rectangles to vary, then you can't do that. You can't say delta x is anything. It's no longer n divided by the b minus a, or b minus a divided by n.
A minute ago when you were saying that the rectangles could be any shape, that you were saying that in relation to what?
In theory, when you break up this area under the curve in rectangles, it turns out that it doesn't matter if each rectangle is the same width.
Okay. That's just related to n going to infinity, or?
Yes.
Okay, okay.
Yes. Okay. In other words, when you're looking for an exact value, this works. Even though I got skinny rectangles, I got fat rectangles, I can't any longer use this, and I don't know how to prove this, because I wouldn't even know where to begin, to be honest.
But as long as for each of those rectangles you take an independent area, it would give you the...
Well, as long as you're letting delta x go to 0, or if you're letting n go to infinity. I think that's the key. As long as n goes to infinity, then it no longer matters whether you're using left-hand endpoint, right-hand endpoint, or a constant delta x. You can be using delta x. What?
They're pretty much just almost lines, just go exactly up to the curve at that point.
Right. So, in other words, as n goes to infinity, all of the widths go to 0.
Right, I see.
So, but how you would do a rigorous mathematical proof of that, I don't know. I certainly don't know how you would do it using this definition, because this definition starts right off the get-go defining delta x, and you wouldn't be able to do that.
Yeah, that's what you're saying. Right, right.
So there must be something else involved there. But thank goodness I don't need to have to do that. But this is something that I'm glad I learned. I'm glad we've done 3 sessions on this. I know how to do this now.
Okay.
And I think that's probably even an important thing for you to know how to do, given that this is the fundamental definition of area under the curve. This is more fundamental than the fundamental theorem of calculus.
Right, that's
I
because that's
think.
based on this, right?
I'm not real sure which came first. I suspect this came first, and this led to the fundamental theorem of calculus. Even though maybe they came out, somebody figured out that the area under the curve was capital F of B minus capital F of A.
And then somebody could have proven it using this.
Right. In other words, somebody could realize that this produces the perfect area under the curve every single time, so that's the fundamental theorem of calculus, but the rigorous mathematical proof may be this part,
Yeah, I see.
using the limit definition. Because like differential calculus, they came up with the power rule, the product rule, the quotient rule, and the chain rule, but each one of those had to be proven using the limit definition of derivative. In other words, the f of x plus h minus f of x all over h as h goes to 0.
Oh, right.
Each of those four rules came from that. So I'm kind of thinking that this fundamental theorem here came from somebody doing the proofs using the limit definition. Or maybe, and it might have come vice versa. I remember reading in the calculus book that they accepted the integral for years without anybody doing a rigorous proof of it. Quite unlike mathematics. Mathematics usually doesn't proceed like that. Usually somebody does the rigorous proof and then they accept something as true. But in this case, they actually accepted the truth before somebody did the rigorous proof.
Right. Could be that's what happened.
Yeah, it could be. It just did happen like that. And Riemann's brilliance. And something else about Riemann. He lived around 1860. Not only did he do the rigorous proof here, but it's his formulas mainly that Einstein used to do his theory of relativity.
Oh, wow. Okay.
Yeah, his foundation was Riemann's formulas, along with Maxwell's. Everybody usually credits Maxwell. In other words, Einstein used Maxwell's formulas to come up with things like the speed of light is a constant everywhere. And Maxwell's formulas pertain strictly to electromagnetic, and I don't even understand them. They look like something like this. I don't even know. I saw somebody on Modern Family, one of the girls was wearing a t-shirt. In fact, I'd love to get this t-shirt. And the t-shirt said, and God said, and then it gives the four Maxwell theory. They're very, very short, simple equations, much like Einstein's E equals mc squared. Very, very succinct. But there's 3 or 4 of them. And so it says, and God said, and it gives the 3 Maxwell theorems, and then the very end says, and there was light.
And there was light. I see.
And there was light. In other words, God said Maxwell's theorems, let there be light. Because light comes from, light is electromagnetic.
Yeah, any kind of electromagnetic.
Yeah, so it's kind of follow Maxwell's theorems.
No, I don't think anybody would write off. I suppose if you're onto a theoretical physicist or somebody, that guy might know what the T-shirt says, but I don't know that many people would know right off.
No, well, I've heard of Maxwell's theorems and I've seen them, but I have no idea what any of the notation means. None of it. I don't know if it's a measurement of the power of light or the intensity of it or the temperature of it or. Oh, you know what? They're not deltas. They're this. It just occurred to me. They're upside down deltas. That's what they look like. And I don't know what that means. I have no clue as to what that means. But that's like if you looked up Maxwell's formulas, they would all have this symbol in them.
Must tell somewhere.
No, it'd be worth looking up. But I hadn't realized the deep connection between Riemann and Einstein until I read this little thing in this book that Einstein used an awful lot of Riemann's formulas.
Somewhere it said, like, I think maybe one of those Taleb books was talking about Poincaré. Also, apparently
Uh-huh.
had similar formulas that were quite similar to the theory of relativity formulas, but like I guess he wasn't one to try to take credit or something like that, you know.
Oh.
So I guess Einstein mostly gets, you know,
Yeah,
credit for it.
I actually I'm always a little disappointed when I read that Einstein based his theory on somebody else's work.
Yeah, yeah,
Because we're all taught that it was this moment of brilliance that no other human has ever had. And Einstein just kind of came out with it, and it was so far beyond the pale that it gets 100% credited to him.
yeah.
But in
Well,
actuality, he's using Maxwell's and Riemann's stuff.
I guess it's on how you put it together, really.
Yeah, I suppose. It was a pretty big leap, I have to admit. In other words, wouldn't you like to be somebody that could go back in time to Riemann's time and said, this scientist came along, took your formulas, and turned it into E equals mc squared, and all of the other stuff that goes with relative physics. I mean, that would be some moment to see what Riemann thought of that, or even Maxwell. It'd be if you could go back in time and talk to both of them and said, this is what your formulas led to. The atomic bomb.
Ooh, not good.
That's a pretty good show. I think I told you on Nova. Called The Bomb. Well worth watching. But
Oh yeah, I didn't see that. I downloaded one. It was I guess it was called American Genius, and it was all these guys that had rivals somewhere else.
mm-hmm.
So it was either here or somewhere else. So it was
I've always mistakenly believed, and in fact, I've kind of always given Einstein credit for winning the war. Because he's, in all the biographies I've seen on Einstein, he is given the credit for writing the letter in 1939 to Roosevelt saying, you need to start a crash program to develop this bomb because if you don't, Germany will get there first. And Roosevelt took heed and immediately started the Manhattan Project. So without Einstein's letter, it probably is quite possible that the United States would not have developed the bomb first, and that certainly would have changed the outcome.
Einstein opt out, though, of that?
What's that?
Didn't Einstein opt out of the Manhattan Project?
Well, no, but here's what happened, is it wasn't really Einstein that wanted to write the letter. It was some German physicist that had actually discovered that, yes, you can split the atom and it will work. In other words, this other physicist first realized that a bomb could be made. But he was little known. And so he couldn't write a letter to the President of the United States and get any results. So he goes to Einstein first and he says, will you add your name to this letter? And he did. And that's what caused Roosevelt to start the Manhattan Project. Now, once they developed the bomb and Germany surrendered, there was a large group of scientists that wanted to disavow the work and not use the bomb. And Einstein may well have been on that list. I don't know.
I see. Because I thought it was as they were developing the bomb that Einstein opted out and Oppenheimer continued and stuff. Maybe
I bet not, because before we actually developed the bomb, everybody thought that Germany was quite close to doing it.
So maybe not then.
Well, you certainly wouldn't think he would. I mean, if he went out of his way to warn Roosevelt to develop it before the Germans do, you wouldn't think he would back out philosophically before he knew Germany was defeated. It was Germany got defeated. Germany surrendered in like March or April of 45. Oh no, of actually 44. Yeah, they surrendered like 6 months before we got a working bomb. And so in that final 6 months, maybe that's when Einstein said, we should stop work now. We don't need this bomb anymore.
Oh, I don't know. I just thought I saw it on some show, but I may be
Well, I
just
think you're
mistaken.
right. No, and I know Oppenheimer was on that list. I just don't know how soon they came to that decision. I don't know if they actually came to that decision before we dropped the bomb on Hiroshima or not. Uh,
Yeah,
I think during the late 40s and early 50s, most of the physicists kind of realized that they had created a monster,
yeah, right.
and it was fine to win World War II, better than having a world run by the Nazis.
Yeah,
But still, the dragon or the Pandora's box was open. But
yeah.
that show, The Bomb, really goes through all that history. It's very fascinating, really.
I wonder if I can find it on there. What show was that? What channel was that on?
What was on Nova?
Oh, on Nova
Yeah, it was
itself.
one of those Nova.
Oh, I bet I
It was
can
a
find it.
PBS special, and it's just called The Bomb.
Huh, I bet I might be able to find that
I'll
then.
bet you can. I'll bet you can. And it's like 2 hours, but just really cool. Of course, I've always been fascinated by bombs. When I ran the Key Club in high school, what we did every week was I went to the library and rented films of nuclear explosions. And that's what we did for our Key Club meeting every
Uh-huh.
every week, was to sit there and watch these explosions after explosion after explosion. And there was something quite fascinating about watching these things.
Wow.
I loved it. I mean, I was the one that I chose what to do. I was the president of the club, so
Huh.
um,
That's cool.
yeah. But so I've always been kind of fascinated. In fact, I was really fascinated when this bomb went off in China the other day, because
Yeah, you were talking
well, they
about
happen
that.
to have video of it. There's cameras, automatic security cameras, and this thing was monstrous. I don't know if you've seen it or not, but it looks like a nuclear explosion. It's the largest explosion I've ever seen that was non-nuclear.
Yeah, that's what you were saying. It
Yeah.
was like massive.
Well, and the death toll is now over 100, and the injured is like 1,000. But if you've seen
Jeez.
any pictures of the area 1 mile away, it demolished everything.
Wow.
There's a whole parking lot full of cars that are just like a nuclear bomb went off.
So do they know what caused it at all yet?
Yeah, I heard something on TV today. They're still trying to figure it out, but they were storing some sort of some chemical that was an explosive chemical.
Oh, wow.
And they were illegally storing more of it in one place than they should have been.
Uh-huh.
They have laws that you can't store more than a certain amount, and now we know why.
I guess so. I just went to my dad's room yesterday to say hi. He was watching this 60 Minutes or something, and it was like
Oh
the
yeah, I
China,
saw it. It was the 50th
yeah,
anniversary.
touring.
Yeah,
Yeah.
yeah,
And it
or the
was like
70th anniversary, not the 50th, the 70th.
60 Minutes, really?
Yeah, no, I mean the 60-minute segment was about the 70th anniversary of dropping the bomb, and
Oh no, I was talking about another one where they're in China. It was
oh,
just thinking about all the toxic stuff that comes out of there.
oh yeah, yeah.
They had the fluorine
Yeah,
coming out of
well,
there.
and that's, of course, one of the bigger problems of that blast in China wasn't just the immediate blast and its damage, but the fact that it was a toxic plume of,
Uh-huh.
deadly chemicals, arsenic and sulfuric acid and stuff that you couldn't really be in. So they had to evacuate the area, and they'll have to leave it evacuated for a while till it dissipates.
Well, this was actually I think it was 60 Minutes. Well, I don't know. Does Anderson Cooper ever do segments
Uh-huh.
on there?
He does, yes.
Okay, it must have been. Well, it was about lumber liquidators here in the
I
U.S.
remember seeing that also, yes.
Yeah, yeah, and now they're like, I mean, a lot of companies to save
Uh-huh.
costs are using like,
Right.
I don't know if they were aware or not or
Low
what. Who knows?
standards, yeah, yeah. I think the
But
Chinese government tries to crack down on that because that kind of publicity is deadly for China. I mean, it's like, remember back when they discovered all the lead in the toys?
yeah, right,
Well,
exactly.
and lead in the pet food, or arsenic in the pet food from China. God, there
Right,
was a time where if you're an American, you wouldn't have wanted anything from China.
right.
They had such shoddy regulations and stuff.
Yeah, I wonder if this is going to have any. Well, if you have floors from them, I guess it would certainly have an impact.
They had to close a Toyota factory that was nearby that was making cars, but for how long, I don't know. Yeah, this is a big city. This is like the fourth biggest city in China. This is a city that's twice as large as New York City.
Wow.
Who knew there was a city that we never knew the name of that was twice as large as New York City on the planet?
Yeah, oh yeah, I believe it, man. We don't know.
Tianjin, China? Yeah, I mean, if you'd have told me Tianjin, China, I wouldn't have known what you were talking about. 14 million people.
By population, you mean?
Yeah.
Oh yeah, I'm sure India, China. I mean, those places are so populous that
Yeah.
yeah, that's not too shocking. You got a couple of billion people living in there.
Yeah. Yeah. All right. Well, I think we're done with sigma.